Okay, welcome to Operating Systems Lecture 15. So let's review the virtual memory subsystem as we have been looking at it. So when you boot up the machine, we said that we start in the physical address space, right? And so if you use address x, then it just, if x is less than m, then you hit the physical memory at that address x, right? You straight away hit the physical memory. There is no translation involved. If you try to hit a physical memory address that's greater than the available memory, let's say capital M is the amount of physical memory available in your system, then it will throw in an error. So that's not valid, right? So at boot up you have this simple system where there's almost no virtual memory subsystem, and it's completely flat from 0 to m. Of course, recall that we boot in 16-bit mode, so segmentation works in its primitive form where you can add the segment register after multiplying it by 16 and all that. But for all practical purposes, our kernel that we are studying sets all segment registers to 0, so you have a flat address space from 0 to m. Then as soon as you enable segmentation in 32-bit mode, so you switch to you enable segmentation, you initialize a global descriptor table, and you switch to 32-bit mode. The moment you do that, all your addresses are now getting translated through the segment hardware, right? Each instruction has a default segment, right? So for example, if you are just making an access through some register, then the default segment is DS, right? The instruction itself, EIP, the instruction pointer itself always goes through CS and all that. So in theory you could enable segmentation and you could use segmentation to segment your address space, but in the kernel that we are studying, it just sets base and limit to 0, base to 0 and limit to 2 to the power 32 minus 1. So once again I have a completely flat address space, right? So if you say I want to access address x, so let's say you fill in the value x into your EIP register, it just goes into the physical memory at address x, and as long as it's between 0 and m, you will see a valid byte. If it's greater than m, you will see an error, right? Some kind of an exception will be thrown by the hardware. Similarly, ESP or any direct addressing. So these addresses can be generated in many ways, through a register, through direct addressing, through displaced addressing, right? All those things we have studied already. Right? In any case, they all go through segmentation, and we saw that after enabling segmentation, our address space is still the same, 0 to m. Okay, so here's another figure. So after enabling segmentation, I had 0 to m. Now the boot sector operates in this mode where only segmentation is enabled in 32-bit mode, and in that mode the boot sector was living in the first 512 bytes of the disk. So the boot sector has code to load the kernel. The kernel lives from the sector number 1 till some value, and whatever that value is known to the boot sector. The size of the kernel is known to the boot sector, and so the boot sector loads that many sectors from the disk and puts them in memory. While it's doing that, the address space is still 0 to m, right? So it picks up the kernel and sticks it somewhere here in this area, right? We saw last time that it sticks the kernel starting at address 1 MB, right? So it starts pasting the kernel starting at 1 MB, and from there on it pastes the kernel. And recall that the size of the kernel wasn't very big either. The size of the kernel was, if I remember correctly, definitely less than 1 MB, right? So you start the kernel from 1 MB, you pick the kernel from the disk, stick it at physical address 1 MB, and it will at most go till 2 MB, right? All the kernel code and the kernel data. Also recall that the kernel itself has been compiled with virtual addresses. So all the symbols inside the kernel image have virtual addresses associated with them. So if I say I want to branch to main, the address of main will be a virtual address, right? It will be a virtual address in the sense that it will be an address above this value 8 and 7 zeros, which is also called kern base. In our code, this is called the kernel base, right? So all the symbols in our image have addresses above kern base or above 2 GB. So all the symbols in that have addresses above 2 GB. So anytime I dereference a symbol within my kernel code, I am going to be trying to access a region above 2 GB. But in this address space, it's not possible, right? Because assuming m is less than 2 GB, if I try to dereference a symbol in the kernel image, I'll see an error, I'll see an exception, right? So not possible at this point. So the boot sector, so what the boot sector does is it loads the kernel and it jumps to the first instruction of the kernel, and recall that the kernel was stored in ELF format, so the boot sector knows exactly where to start, and so the kernel, the first instruction of the kernel gets started, and the first instruction of the kernel lives in this file called entry.s, right? Now the first few instructions of the kernel entry.s are going to execute in this address space. So these instructions have to be very careful, they shouldn't be dereferencing any kernel symbol, because all kernel symbols have addresses above 2 GB, right? The moment it dereferences the kernel symbol, I'll get an exception. It's not legal in this address space, right? So the first thing it does, the entry.s file does, is it changes this address space by enabling paging, right? So it enables paging, and it uses a page directory called entry page directory, right? And we saw last time that this entry page directory implements an address space where the first 4 MB are mapped identically. So if you access an address X within 0 to 4 MB, you will hit physical memory at address X, right? On the other hand, it also maps this address kern base to kern base plus 4 MB to the same location 0 to 4 MB, right? So if you access address kern base plus X, and assuming X is less than 4 MB, then you will hit physical address X, right? So that's how the entry page there was configured, and so the entry.s code just switches from this address space to this address space as soon as it enables paging and sets up CR3 to point to entry page there, right? So it points CR3 to entry page there, enables paging, and suddenly I'm running in this address space. Recall that because the kernel itself, all the instructions, the entry.s file itself was living in less than 4 MB space, so we said from 1 MB to 2 MB, let's say, all the addresses, the EIP and ESP still remain valid, because the addresses from here are identical here, 0 to 4 MB, right? So those remain valid. You don't, it's not like I'm standing on the ground and the ground has been taken away from me. It's not true, because as long as the kernel is less than 4 MB, the kernel is safely mapped, right? So the next instruction can execute. All right. So you enable paging, but you ensure that the ground that I'm standing on still stays as soon as I switch the address space, right? Okay. But in this new table, there is an extra mapping, and this table is going to be used to switch from here to here, right? Recall that the kernel, all the symbols in the kernel have values which are in this range. So I shouldn't be dereferencing any symbol from here. The only thing I'm going to do is I'm going to look, so in this there are some symbols, like there's a region that's allocated as stack, right? So we saw, so let's look at the entry.s file, okay, on sheet 10, and if we'll see, there is this instruction which is loading this value stack plus k stack size into ESP. K stack size is a constant, stack is a symbol that has been declared here, right? So stack is a symbol in the kernel, and recall I'm saying that all symbols in the kernel have been compiled to have addresses in the kernel's virtual address space, which is above kern base, right? So the stack, the value of stack will be some kern base plus something above kern base, and so that plus k stack size is, let's say 4096 bytes, so that variable is loaded into ESP. Recall that at this point the paging has already been enabled, so this address should be a valid address. I should be able to dereference ESP because I'm operating in this address space, right? In this address space, ESP will be pointing somewhere here, and so when I dereference it, I'll get the right value, right? So I was able, so notice that I've only started reading the kernel symbols after I enabled paging. Before I enabled paging, this code did not read any kernel symbols, except that one kernel symbol that was read was entry page dir, but it was converted to its physical address before it was loaded into CR3. In any case, CR3 is going to take a physical address, so it's okay, and physical address is already mapped, right. So this piece of code in entry.s is very carefully written. There is some amount of tricks involved in this kind of code, and this kind of tricks you can only see if you are actually looking at some kind of real code, right. So it if you find this interesting, you should probably go and single step and see exactly what's happening. As soon as you turn on paging, what addresses become valid, what remain invalid, what were valid earlier and have become invalid now, what were invalid earlier have become invalid now, etc., right. So it's interesting. Okay. And then you basically so at this point though you don't need to do any conversions from V to P, right, because stack having an address above 2 GB is a valid address. You are already in the new address space. Similarly, main is a kernel symbol which will also have an address which is above kern base, and what you're going to do is you're going to jump to main, right, and the moment you do that you have reloaded your EIP with a kernel virtual address which is above kern base. So you loaded ESP with a kernel virtual address here appropriately, and here you're going to load the EIP with a kernel virtual address, okay. So at this point, so far my EIP and ESP were pointing somewhere here. I reloaded ESP to point here and it's standing on solid ground, and then I jump to main and once again EIP now points here. So now both my ESP and EIP point here, and from now on I'll basically be executing in this space completely because I've forgotten about all my addresses here. Anything I dereference from the kernel will have addresses in this space. So from now on I just execute in this space, right. So from now on it's just normal plain C code that can execute, just plain dereferencing should work, right. But this kind of tricky code had to be written in assembly because C doesn't understand this different address spaces and all that kind of stuff. It's very tricky. The programmer has carefully done this, very carefully done this. Okay. All right. So we said okay, let's look at so it's now going to jump to main, and here is the code for main, right. And main is this long function that that we don't necessarily need to go into full detail of, but the important thing to note here is that this is the first instruction that will get executed, and at this point the stack has been initialized correctly, right, with some size, stack size, k stack size. As long as these functions don't overflow the stack, right, don't use too much stack space. For example, they don't, the function called depth is not very large ever. They don't allocate local variables that are too large or too many local variables. That stack should be sufficient to implement all these, to execute all these functions. Okay. All right. So the first function it calls is kinit1, and so this is a physical page allocator. All right. So it's going to initialize functions called kalloc and kfree that allow you to take physical pages from the available address space. We're going to study this later, but let's just assume that this function works correctly, and after this function has executed completely, the kernel can make calls to kalloc and kfree, right. Kalloc is just like malloc for kernel, so just you can allocate memory and you can free memory, except that kalloc only works at page granularity. So malloc can take any size, but kalloc can only one kalloc call will allocate one page and give it to you. Okay. And then there is this function called kvmalloc which will initialize the kernel page table, and that's what I'm going to discuss today, right. So we said that this is the page table after entry page dir, and what the kernel wants to do is that it wants to remove this space and map this space completely into physical address space. So right now only the 0 to 4 MB region is mapped. You want to map entire 0 to M in this area, right, and you want to remove this so that this can be used for user pages, right. Recall that was what the XV6 paging configuration was. Okay. So Okay. So in this kernel page there, so let me call it K page there. I want to switch from this address space to this address space, and so what I'm going to do is I'm going to map, right now it's just 2 GB plus 4 MB, I'm going to map the entire physical memory from here, right. So I'm going to say 2 GB plus M, right, and this is entirely going to go to 0 to M in physical memory, right. So that's what I want, and how are we going to do it, we're going to look at the code later, but let's just see what we want, right. We want to map the entire physical memory here. Also recall that the first 1 MB was reserved for memory map devices, right. The first 1 MB of physical memory address space is actually not memory, it's console and other things. So even that gets mapped, but that's just reserved for the memory map devices, right. Also recall that I loaded the kernel at 1 MB, so this is, let's say, mmap, let's say mmapd, memory map devices. Then there is some area which will be loaded for the kernel. Recall that we had loaded the kernel starting at 1 MB of the physical address space. So starting at 1 MB, you're going to have the kernel, both code and data, right. And then all the other space, I'm going to call it free space, right, and that's the space I'm going to manage using kalloc and kfree. So that's the space I'll say, okay, this is space that you can use for your heap, right, or this is a vacant space, and this is the space that you can allocate for your data structures, like the page directory, right. So where is the page directory going to get allocated? Recall that the entry page directory was a global variable, and so that was allocated in the data section of kernel, but anything other than that, for example, per process page directories, right. So all these things are going to be allocated from this extra space, which is wherever the kernel ends, and from there on till whatever capital M is, the physical size of physical memory. Also this is the place where you're going to allocate memory for data structures like process control blocks, right. And most importantly, this is the space from where you're going to allocate memory for the user processes themselves, right. So what you're going to do is you're going to say kalloc, you're going to get some page, and you're going to create a mapping in this area for that. So recall that's how it works. You basically allocate some page here. Let's say a user says I want more page, or a user says I want to load a particular executable, and that executable is larger than the current allocation of the process. What it's going to do is it's going to create mappings here, it's going to allocate some space from here. Whatever space it allocates from here, it will have some backup in physical memory, right, some pointer into the physical memory. So whatever pointer I get from allocation here, I'm going to convert it into its corresponding physical address, and then create a mapping from here to that physical address, right. Recall that the entire memory has been mapped here. So the entire memory has been mapped in my virtual address space. I allocate some area from that virtual address space, I get a page, I convert the address that I got to its physical address, and then I create a mapping in the user side of things to point to that, right. So these pages which are mapped in the user side actually have two mappings in the page table, one on the kernel side and one on the user side, right. So the two names for the same physical location, one name will be kern base plus something, and the other name will be whatever the user wanted to allocate it, wherever it wanted to allocate it, okay. Alright, so okay. So I want to switch from this organization to this organization. Also I'll point out that the top, there is a slice of virtual address space on the top that starts at 0xFE and 6 zeros till 0xFF, right. This slice of address space is actually used for memory map devices also. So just like this area is used for memory map devices, this area is also used for memory mapped devices, and so this maps identically to the physical address space F is same thing, right. So basically the physical address space on a 32-bit x86 machine, the physical address 0xFE and 6 zeros is not actually pointing to memory, it is pointing to some memory mapped devices, and the kernel wants to retain that access. So what it does is it just says the top virtual address space maps identically to its corresponding physical address space. So if the kernel ever wants to access those devices, it can just access it using that address, the same address, right. So basically I am not going to use this top address space from FE00 0000 to FFFFF for anything other than memory mapped devices, right. They map identically to physical address space, right. So just to make this discussion more complete, at boot up the address space wasn't just this, right. Actually at boot up the address space was 0 to 1 MB is devices, 1 MB to M is whatever your physical memory is, and also there is some chunk on the top F E 6 to F F. This area can also be accessed, however this will also point to devices, right, in the physical address space. So that was the original physical address space. So the amount of physical memory that you can have in your system is not really 2 to the power 32 minus 1, it is 2 to the power 32 minus 1 minus 1 MB minus whatever this is, okay. And so what the kernel wants to do is now retain this access, and so it is going to map this identically to the corresponding physical address space, right, that is all. Anyways, that is not really important, but when we are looking at code it will help us in understanding what is going on. Okay, so let us look at what is kvmalloc doing on sheet 17. Okay. So basically at the highest level kvmalloc is going to initialize a new page table which is going to have this kind of mapping, right, and it's going to switch to it, and it's going to forget about the old page table, and that's it, right. So the kvmalloc function is just 2 lines. It calls a function called setup kvm. This is going to initialize a new page dir, kpage dir, which will have this address space mapping, and it's going to return a pointer kpage dir to that particular page directory, okay. So it's going to initialize a page directory. Where is it going to get the pages for this page directory? From its heap, right, from all this area that we discussed, this extra area, this is the kernel's heap. So it's going to allocate a page directory from here, and it's going to initialize it, and it's going to return a pointer to the page directory, okay. That return pointer will be a virtual address in the kernel space, right, because everything in the kernel from now on is in the virtual address. When you allocate a page, the return value that you get is also a virtual address. So if you want to convert it to a physical address, you need to subtract kern base from it, 2 GB from it, right. So this function is going to allocate a page table and return a pointer to it. This pointer is going to be a virtual address, and then I'm going to call switch kvm. So kpage dir happens to be a global variable, okay, and so you just set up kpage dir to this, and switch kvm is just going to load cr3 with kpage dir, except that it's going to call v2p on kpage dir before it loads it into cr3. Perfect. You allocated kpage dir in your virtual address space, initialized it, you got a virtual pointer, you convert it into physical pointer and load it into CR3. Recall that CR3 takes only physical pointers. Okay. So that's very simple. What we're going to look at next is setup KVM, how exactly this page table is getting initialized. Alright. So what is the structure of this page table? Okay. So on the same page at line 1737, here is the code for setup KVM. Alright. And what it's doing is, it first calls kalloc function to get a page from the kernel's heap. Right. So let's just assume that kalloc just allocates a page from the kernel's heap and returns a pointer to it. Right, just like malloc, and puts it into pageder. Just in case the malloc failed or kalloc failed, then it just says, oh, I can't proceed, it will return 0, and ultimately it will return 0 and tell the user that something has failed. Why could kalloc fail? Give me some reasons. You have run out of memory. So let's say the physical memory was very small, and so the headroom that you have above the kernel space is very small. So when you call the first kalloc, the first page itself got failed. Right? Yes, question.
How is the kalloc working? Like right now we do not have a page title or anything. So from where will it allocate a page?
Okay, so there was one function called kinit that I skipped. Alright, so I'm going to discuss that later. But let's just assume that this address space has already been initial. So this right now we are working in this address space, right? 2 GB to 2 GB plus 4 MB. So that's a great question. Assuming that there is some headroom above the kernel in this first 4 MB, I should be able to allocate a page. Right? So it's not really limited by the size of physical memory at this point. It's actually limited by 4 MB, this artificial limit that you've used, right? Because you've only mapped the first 4 MB. So assuming that if the kernel size was so large, if the kernel was let's say 3.9 MB, then my kalloc would have failed, right? Irrespective of how much physical memory I have. So if my kernel was indeed that large, I should have mapped more area here in my entry page there. But my kernel is really small, right? Not that large, let's say less than 1 MB. So I have enough space. So when you call kalloc, you're actually allocating space from here. Okay, because yeah, you're right. At this point, I've not switched. I don't have a heap. My heap is actually very small. So what you have done is he has just initialized whatever space is here to a heap, and that's where he's going to serve his request for kalloc. All right. Okay, so he's going to get a pointer in that kern base to kern base plus 4 MB space, and that's going to be stored in pageder. The next thing it does is it zeroes out the pageder. So the pointer that he gets has a 1 page size memory area that can be used, right? So page size is 4096 bytes, and recall that our page directory structure itself was 1 page, right? So 4096 bytes, and so what it does is it just zeroes out. So memset pageder 0 page size means zero out the entire page. What does it mean to zero out the entire page directory? Basically means no mapping exists, right? Because recall that for a mapping to exist, the present bit in an entry should be set, right? So if you zero out the entire thing, none of the present bits are set, and so there are no mappings in this page directory initially. Okay, we can ignore this. This is just an error check, but then it's going to say for k is equal to k map, k is less than this, map pages, right? So it's going to, so k map is an array of mappings. It's going to look at this array, and it will call the map pages function to create mappings in the page table for that array. What this array is, k map, is basically telling you what are the regions that need to be mapped. For example, so it basically, so static struct k map, it says this is the virtual address at which you need to map a region. This is the corresponding start physical address at which this region should be mapped. This is the end physical address, so it also tells you the size of the region that needs to be mapped, and these are the permissions with which you should map it, right? So for example, what we want to do is we want to say 0x, this kern base 2 GB value, so 2 GB value to this 2 GB plus 1 MB should be mapped to 2 GB plus 1 MB with all privileges, read, write, execute. Then 2 GB plus 1 MB to whatever the kernel code is and read only data is, that should be mapped to 1 MB to 1 MB plus whatever kernel size is in read mode. You don't want that the code should be writable, just a precaution measure. So you just basically map it in read only mode. And then for everything else, which is kernel's data and all the other memory, that should be mapped in read write mode in this area to the corresponding physical address, right? And finally, this address 0xFE00 should be mapped identically to the same address in physical memory. So those are the 4 sort of regions that you need to map, right? 4 contiguous regions that you need to specify, and that's what this array is telling you, right? So the first mapping is saying start mapping at kern base, which is 2 GB, physical address 0 to physical address 1 MB, extmem is 1 MB with write permissions, alright. So it's just initializing the IO space. It's saying kern base to kern base plus 1 MB, map it to physical address 0 to 1 MB with write permissions. This is my IO space, memory map devices. Then the next thing I have is starting at kern link. So kern link is what? It's going to be the place at where you will start the kernel, which is 2 GB plus 1 MB, okay, and V2P kern link is 1 MB. So recall that we had loaded the kernel starting at address 1 MB. The boot sector had loaded the kernel starting at address 1 MB. So you're going to load the kernel starting at 1 MB at address 2 GB plus 1 MB, okay. The size, the endpoint of this particular segment will be determined by where the data starts. So the kernel has been organized the kernel's ELF has been organized in such a way that this is kern base plus 1 MB, that's the start address. It will first have some code, whatever the size of the code is, and so somewhere the code will finish. Let's call that position X. Then there will be some area which will be called read only data. Okay, you can specify read only data. For example, in C, if you say const something, then declare it as a global variable, that gets allocated in the read only data, right? So let's say that goes at Y, and then everything else is, let's say, data, right? So there are pointers in the kernel. When you compile the kernel, there are symbols in the kernel which tell you that here's the data, here's the read only data, and so on. So this Y is pointing to, so that's where the data pointer is pointing. So what the loader is going to do is it's going to consider this as one segment and map it with read only permissions, right? And it's going to map this and everything above it. So above it is basically heap. After you load it, above this is heap, so everything above is going to be mapped with read write privileges, right? Okay, so that's what's happening here. Kern link, V2P kern link, which is 1 MB to V2P data, right? So wherever data starts, till that point, you map it with 0 permissions. 0 means read only permissions in this case, right? If it's writable, then you say PTW. If 0, that means read only. And then starting at data, map it from at V2P data all the way to physstop. Physstop is the size of the physical memory, let's say, right, or the maximum size of physical memory that you will support. So all the way up to fizz top, you map it with writable permissions. So that's kernel data plus all the other memory that will be used as the kernel's heap, right? And then you map dev space to dev space, which is just FE00 identically, right? So that's what you're going to do. You're going to read this array, which has this these mappings, contiguous mappings in a nice readable way, and for each of these mappings, you're going to call map pages, right? So what map pages is going to do is it's going to create these mappings. Map pages takes an argument, a virtual address, the corresponding size, which is given by fizzend minus fizzstart in the kmap structure, the corresponding physical address at which it should be mapped, and the permissions with which it should be mapped, right? So it first takes the page directory in which it should create the mapping. It assumes that the page directory should already be created. The virtual address, size, physical address, permissions, and if it succeeds, then it will return a non-zero, a positive value greater than or equal to 0 value. Otherwise, it will return a negative value. What are some reasons for why it can fail? Recall that to map pages, it may need to allocate more pages, right? Right now, you basically have a page there. So this is the page there that is initially completely zeroed out, all zeros. Now let's say I want to map address 100 to 1000 to physical address 0 to 900, just a hypothetical example, right? So I want to map virtual addresses 100 to 1000 to physical addresses 0 to 900. What do I need to do? I'll say, okay, address 100 is represented by entry number 0, right? Each entry here represents a 4 MB region, right? Because these are 2 to the power 10 entries mapping a space of 4 gigabytes, right? So each entry, one entry is mapping 2 to the power 32 divided by 2 to the power 10, which is 2 to the power 22 address space, which is 4 MB, right? And recall that this 4 MB could be mapped using large pages, or it could be mapped using another level of indirection using a page table, right? So in this case, 100 is going to be this, the first entry within the first 4 MB. You're going to allocate another page table here. Let's call this page table, and in this you're going to say each entry is going to allocate 4 kilobytes. So here you're going to create an entry saying map to 0 to 900, right? Clearly I cannot just create this mapping, I need to say what is the corresponding pages, and so I can only do this at page granularity. So instead of 0 to 100 to 1000, I'll probably have to say map page 0 in VA space to map page 0 in PS space. Okay. So this is just going to map to 0 in this case with the corresponding permission. So to be able to do this, so for this kind of mapping, I need to potentially allocate a new page to store this mapping, right? And so this allocation could potentially fail. So page directory is the top level structure. Recall that our page table is a 2 level structure, and so whatever I want to map, I may need to allocate pages for the second level. And so if that allocation fails, if I'm running out of memory, I can probably fail. So that's one reason, for example, why map pages could fail. Okay. Yes.
So what do you mean by, like, we are mapping all the memory from my data to my physical stop? So it means that I will divide that chunk into small pages and map it in my page.
Yes. So if I want to map, let's say 0 to fizz top in one go, I will divide it into chunks and create entries in the page table, because recall that I cannot just, the paging system doesn't allow me to map all at once. I have to divide it into either large pages or small pages, and then create appropriate entries in the page table to create that mapping.
But sir, we are trying to map the complete physical space to the complete physical space, so there will be not enough pages for the other small chunks which we are giving. Like if suppose that if you are mapping from data to the complete top of the physical stock, if you are dividing into all pages, small pages, and mapping into the physical pages, in the small chunks of say 1 MB, then where will we get those pages from? Because
Okay.
we already mapped those pages.
So the question is that let's say I want to map an entire region from data to phystop in the page table, right? Question is how much space do I need to map this? The amount of space that I need to map this is basically whatever the space is divided by 4 KB if you are using small pages, right? So that's not that much. So let's say this space was, so the overhead is basically less than 1% or less than 0.1% actually, right? So whatever the space was, let's say the space was x bytes, then the amount of space that you require to map those x bytes is x divided by 4000 roughly, right? So that's less than 0.1% of x.
But when I'm mapping those in the page directory, it means that I have already also have a backup in my physical memory for those mapping.
Could you repeat?
Like if I'm mapping from my data to physical stock
Okay.
in my page directory, then it means that in my physical memory also I have allocated that space for that particular memory only.
You have mapped that memory. You have mapped that memory. You are not, so there's a difference between mapping and allocation. You have just mapped that memory, which means this name is going to refer to this location. You haven't allocated that memory, right? Allocation means you are basically committed to using it. You just mapped it. You're going to use it later on. Okay. The memory that you have allocated is the kernel's code and kernel's read-only code and kernel's data. Kernel's read-only data and kernel's data. All that has been already, there's some contents into it which are useful, which shouldn't be overwritten. So all that memory is mapped, but that's a small piece. Everything above that you have mapped, not necessarily used. You're going to use it later, and you're going to use it using kalloc and kfree functions. You're going to manage it using kalloc and kfree functions.
So we don't need to store that mapping. That mapping will require some space.
Which mapping?
Virtual to physical.
We don't need to store that. So can you say your question fully?
So Shashank was saying that we need some space to store that mapping, that this page number in virtual will point to this page number in physical.
Sure.
So how do we do that?
So how do we say that this page number in virtual space maps to this page number in physical space? We say that using a page table entry, right? So one entry in the page table basically says that this page maps to this page, right? And so an entry of 4 bytes gives you information about mapping for a region of 4 KB. So it's 0.1% overhead of space in that sense. Okay. All right. So what map pages is going to do is it's going to fill in this structure called pagedir such that this area in virtual address space gets mapped to this area in physical address space. Okay, and it's going to do it using small pages. All right. So recall that I had said that one common optimization used in mainstream kernels is that you use large pages to map the entire kernel. Right, that saves space. But XV6 doesn't do that. I mean, it's not so. XV6, just to make things simple, uses small pages to even map the kernel address space. So all these regions are going to be mapped using small pages. Right. In this case, for example, if I wanted to be smart about it, I could have probably said, look, this area is 1 MB, so I'm going to use small pages to map this area because 4 MB pages are too big to map this area. This area from kerneling to V2P data, this is also very small. I said it's less than 1 MB, so even this it doesn't make sense to use large pages. I'm going to use small pages for this. But this area from V2P data to phystop, and assuming my phystop is really large, right, like 100 MB or 200 MB, then this area is potentially mappable using large pages, right? But we are going to forget about it. We're going to say we're going to map in all these areas using small pages, right? And finally, this area is also small, so large pages may or may not help. Yeah, I mean perhaps large pages will help here too, but in any case, we are going to use small pages to map all this.
So FizzTop marks the end of E.
FizzTop is just a constant defined in the kernel, which basically says what's the maximum amount size of physical memory that x86 supports, right? So FizzTop is just set up to hexadecimal E, I think E and 6 zeros, which is 224 MB, right? So it just, irrespective of the size of the physical memory, it maps data to FizzTop identically, okay? So if the physical memory was larger than FizzTop, that area is not accessible, right? Above FizzTop area in the physical memory will not be accessible. If the physical memory was less than FizzTop, let's say the physical memory was only 100 MB, then you have just unnecessarily mapped extra area, but that's okay. I mean, if the user ever accesses that area, he is going to get some error, right? Some exception. Okay, let's stop here.